Okay, good afternoon, everyone. Today, very happy to have Dale Barker. He's the director for the Center for Climate Research at Singapore. Dale has extensive experience with data assimilation research, use of observations in numerical weather prediction, and regional climate models. He led the WRF data assimilation program here at NCAR from '99 to 2009. Between 2010 and 2018, he led the scientific development of the first EU-funded European regional reanalysis. In his previous role, before joining his present position at CCRS, Dale was the Associate Director for Weather Science at the Met Office, the UK Met Office, leading 200 staff working in meteorological R&D and research to operations transition of a global and local NWP model, ocean wave forecasting, air quality, atmospheric dispersion systems. Dale's a fellow of the Royal Astronomical Society, a fellow of the Royal Meteorological Society. He's a visiting professor at Reading University and an NCAR affiliate scientist. He's a previous member of the WMO and WWRP's mesoscale weather forecasting working group. And he chairs the scientific advisory committee for the new KEOPS Korean numerical weather prediction program. So it's a great pleasure. This is a very heroic action on Dale's part, coming in at 4 o'clock in the morning, live from Singapore. And without further ado, let's welcome Dale. Dale, the floor is yours.
Thank you, Rich. I hope you can hear me okay. Yeah. Okay, assume you can hear me okay. Yeah, thanks everybody for coming along. Yeah, I'm Dale. I was at NCAR 2 or 3 weeks ago. Didn't quite get a chance to give this talk in person there. I was confined to my hotel room for the first week of my visit, but there you go. That's modern life for you. Yeah, I'm back in Singapore now. It's 3:30 in the morning, and I'm not going to speak too loudly because the walls aren't that thick in this hotel. So yeah, yeah, welcome everybody. I wanted to spend some time just giving a fairly broad brush talk about what we do at CCRS, the Centre for Climate Research Singapore. It's part of the Met Service Singapore, and I'll cover both weather and climate, but given this is an M-cubed seminar, I'm not quite sure how many climate people will be around, so maybe I'll be dwelling more on the weather side of the house. But okay, on we go. So yeah, I'll just give I'm not sure how many of you are familiar with tropical meteorology in the climate Singapore region, but I'll give a few slides on that. Interesting place to do weather and climate research. Just a bit of an overview on CCRS. And as I said, talk about the weather prediction side, and then just a few slides on the climate change side of the house, which is the dominant thing actually in CCRS, and a few strategic directions. I think we're looking for the sweet spot. We're a relatively small organization. We have about 45 people, trying to take on another 10 at the moment, but obviously we can't do it all. There's a huge amount to be done, so we have to be strategic and prioritize what's really important to Singapore stakeholders and is feasible with the resources we have. So just a few slides on the climate in Singapore. Singapore's a fairly small place. I'm not sure it's bigger than Denver, but it's about 40 kilometers by 20 on the southern tip of the Malaysian Peninsula. It's about 1 degree north of the equator. It's a pretty hot and humid place, and rainfall are the top 3 priorities when it comes to weather prediction. So yeah, so a couple of slides there on the type of weather. Interesting storms, Sumatra squalls, all sorts of weather phenomena, localized convection. This is of course the maritime continent part of the world. And I'll probably come back to it, but it's in the name. That coupling between the ocean and the atmosphere and the land is absolutely essential. So the development of coupled models, environmental prediction, coupling between hydrology, meteorology, oceanography is sort of has to be done in this part of the world. You can't ignore, just choose one component to work on. But it's an interesting place. there's a link at the top of that title there. I can share the slides if you can't see that link in the. Yeah, so every year we produce an annual climate assessment report, which is looking at obviously the latest statistics and the weather, the climate for the year. But there's usually a nice introduction in there in terms of the weather processes, the tropical processes that affect this region. And as an infographic on the right there, Singapore is the little red dot, as it's known around here, the southern tip of Malaysia. So right on the equator pretty much. So you've got a variety of tropical processes coming into play here. You've got the ITCZ, which of course oscillates backwards and forth, north and south of this place. You essentially have two monsoon seasons. One is the northeast monsoon season, which runs from about December to February. Predominant wind directions from the northeast. You can get quite nice cold surges. And if they mix up with the Borneo vortex, then you can get some quite interesting weather coming down there. The other end of the spectrum, we have the southwest monsoon season, which is June, July, August, getting into early September. So again, when the ITCZ is up north, and so that's the time of year where it's actually a drier part of the year. And one of the really interesting phenomenon here is the Sumatra squalls, which kick off along the island of Sumatra here and cross the Straits of Malacca and usually hit Singapore in the early hours of the morning and wake everybody up with some really heavy rain and flash lightning, etc. So, and of course you have the larger scale climatic drivers, Madden-Julian oscillation, you've got the Indian Ocean dipole, the ENSO, all, of course, all influence the climate in this part of the world. We don't really get too many tropical cyclones too close to the equator, of course. But yeah, MJO, ENSO, IOD are the big climatic drivers in this part of the world. So just a couple of slides just illustrating the sort of climatology of the area. The rainfall, as you can see, we've got the monsoon seasons. This is the southwest and northeast monsoon. So the 30-year average of the histograms, you can see fairly consistent 200 millimeters or so average throughout the year. A bit of a dip in February as we get into the intra-monsoon system after the northeast monsoon. But as you can see, 2021 at the dots here, it's actually what the second wettest, and it gets wet here, and this was the second wettest year on record. In terms of temperature, again, as you can imagine, it's pretty warm, pretty humid most of the time. I think it was 10th warmest in the trend, but I think the rainfall in particular was notable over 2021. And again, if you look at when we're looking at seasonal forecasting aspects, we look at El Nino and the IOD in this part of the world, you can see that as you probably know, there was a double dip in terms of a La Nina event, which typically leads to more rainfall in this part of the world. But again, this goes back, this dip down here is October 2020, and then back again about a year later. Doesn't really correlate with the significantly anomalous rainfall. So we don't think it's really that this is a relatively mild La Nina. It's not really due to that. And of course, the Indian Ocean dipole negative index again leads to wetter weather in this part of the world. It's only a very mild IOD for that year. So it doesn't really explain the anomalous rainfall for 2021. But then you get into the Madden-Julian oscillation. If you look at 2 months, the faces the MJO from February 21 and August 21, and I think you can essentially see that this is the predominant cause of this the rainfall. You got the dry Singapore in that phase of the MJO, which correlates well with February in the MJO, and then back in August, further on in August, you get this big peak here. So this is about the MJO rather than the it's of course it's all coupled and linked, but the clearest correlation is with the Madden-Julian oscillation. So some interesting large scale climate dynamic stuff going on in this part of the world. So it's a fairly new topic for me, but it's a fascinating subject to get teeth into. Okay, so that's just a bit on the basic climate of the region. I'll just say a little about CCRS now. So CCRS has been around for about 9 years now. So it's part of the Met Service Singapore. And again, I won't read all the words on the mission, but essentially we're about tropical climate variability and weather prediction in this part of the world. We're part of the National Met Service, so we're not just about publications. We have to deliver to whether it be operational weather prediction or providing climate projections that our stakeholders can use. Singapore, the existential thing about climate change for Singapore is sea level rise. They've got nowhere to go if the seas rise too much. So they really have to plan ahead and look at both inland flooding and coastal inundation. Water is the big thing here, of course, but urban heat is a secondary one, but I'll come to that one. That's a little more in control of Singaporeans than the sea level rises. I'll come back to that one. But yeah, the vision for CCRS is, we want to be a world leading centre in tropical climate weather research, obviously focused on this region. So yeah, it's been about 9 years. I've been in position since August 2020. And I've been working with Singapore, and actually gave a talk on the weather prediction side of this M-Cubed seminar back in 2017 or so, because we did have a project with NCAR M-Cubed as part of this this development of what we call the SING-V numerical weather prediction system. So I'll talk a little about these major focus areas, yeah, I don't have time to go into too much details on any of them. Yeah. So very briefly, so organogram, where's myself there, we have an international science advisory panel, and we have Song Hong if he's here, he's part of our ISAP, as well as Michel Jarreau chairs that one, ex-Secretary General of the WMO, so it's a pretty powerful ISAP. And we have a Department of Climate Research and a Department of Weather Research, and what is known as the Climate Science Research Program Office. So we're not actually just doing our own research. We are given big pots of money, as I'll come to, about 30-40 million of Singaporean dollars that we manage and defray to the local universities to do targeted weather and climate research that is agreed to be a priority to the agency. So as you might imagine, Singapore is fairly well coordinated, and government has a big hold on the purse strings, and again we're part of the government, and so we can play a role there in terms of helping the university community through provision of models, observations, and also steering in terms of research on what the priorities for Singapore are. So again, it's across the whole spectrum at the bottom of the branches, all the way from nowcasting out through 1-2 day NWP, seasonal forecasting air quality, all the way out to regional climate projections. So it's a lot of work for 45 people or so, well, we'll let others judge how we do. Yeah, so the new kid on the block in CCRS is the Climate Science Research Program Office. It was launched in 2020, and as I said, this is about national climate program management, and we have 2 programs. One is specifically on sea level rise research, that's about 7 million. And the new one, which was launched last month at the WCRP Sea Level Rise Conference, which we hosted in Singapore, is the Climate Impact Science Research Program. That's 23 million, looking at the impacts of climate change on a whole variety of sectors. And you see the sectors at the bottom there, so not just sea level rise, but water resources, flood management, biodiversity, food security, human health, energy, etc. So that's a fairly new thing that's going to be kicking off. There is scope for international involvement, but you have to be affiliated and working through a local Singapore university or research institute. So there are more information will come out about that program in the next few months. But it's all about, as it says here, capability building. It's not a large weather and climate scientist community in Singapore. I think everybody pretty much knows each other. I've been here 2 years, and I pretty much know everybody who's in the topic. It's it's a city, so 2 or 3 major universities. But trying to build that community, trying to get the education programs, climate science and meteorology programs in the universities is one of the things we're trying to do, because there are no climate and meteorology courses in the university at present. So we're trying to work internationally with University of Reading, for example, to spin up some meteorology courses and climate science minors within some of the departments. Yeah, so that's the CSRPO. I just got one more slide here, a bit more programmatic, and this is so again, given sort of the way Singapore works, it's very much a sort of develop a national climate science plan, and we'll coordinate it at the national level. and there are many versions of this. We reviewed WMO, WCRP, Met Office, Bureau of Meteorology in Australia. But this is our interpretation of what a national climate science research master plan might look like. So if I can just explain it a bit. At the top, you've got the agencies, the users in the various sectors, such as flooding, urban heat, biodiversity, greenery, public health, the Ministry of Health, etc. And of course, they're all impacts from weather impacts and climate impacts. But as we all know, in terms of the science, the rainfall that affects flooding is the same rainfall that affects moisture, latent heat, urban heat, affects the type of trees that can grow. So, we don't want it to be siloed from the top. We have to deliver to these various agencies, but what we need is a national climate science activity, which is where these horizontals come in. So underpinning climate science, which is going to feed all of these sectors. So, and the sweet spots for us, a tropical urban climate, of course, it's a city in the tropics, and a no-brainer. The complexity of the climate in the maritime continent, given the predictability issues in this part of the world, we really have to have a good handle on uncertainty estimation and risk analysis. And of course, we're also looking at past, present, and future climate, as I said, reanalysis, today's weather, and nowcasting, and then also climate projections out to 2300 for the sea level rise, for example. So again, I look at the enablers here, and I should think of NCAR sometimes when I look at this, the provision of the what they call in the UK, the national underpinning capabilities that you need to do the research. And there are 4 big pots there. You need the observations, you need the models, you need the supercomputing, the IT infrastructure, and of course you need the most important thing, you need the people and the partnerships to make it happen. So there are investments in observations, modeling, IT infrastructure, and people that are being planned to enable us to focus on these research questions, which will provide the answers that the agencies are asking, that will allow them to make decisions and plan for their mitigations or adaptations to climate change. So that's a very brief overview of how the national plan will work. There's around $150 million attached to this at the moment in Singapore. So, I think it's even then, again, this is fairly specialized. We're not doing everything. We're not doing global modeling, for example. We can't do it all. So we have to focus on what Singapore needs. So that's the essential of the framework. And I'm not really going to talk too much more about it, but that's occupying quite a lot of my time personally at the moment to help build that with the agencies and the local universities. So coming back to the science, I'll give a few slides on the weather prediction. I having spent 20 years at the Met Office of my life, I have to use the word seamless at least once in my talk. And this slide is sort of from the Met Office anyhow. So so I think the idea here is, as you may know, we're a partner, actually a core partner of the Unified Model Partnership since February 2022. Singapore is a core partner with Australia, the UK, New Zealand, India, and South Korea. But using the modeling systems with traceable differences is not trying to apply the same model configuration. But if you're going to have differences, you've got to understand why you're making them different, and you've got to be traceable and have good reasons of why you need to do things different. It's not just a random selection of physics parameters. There is only now one physics package for the entire regional applications across the world. There used to be 2. There was a tropical one in mid-latitude, but the past 6 months that's been merged and shown to provide better performance in both weather and climate applications in both mid-latitudes and tropics. And that was a huge effort. That was 5 years of effort for 20, 30 people. But again, the differences now are traceable, and we can, again, if we make differences, it could be resolutions or vertical levels or urban canopies or whatever it might be, then we have a good reason for making those changes for the particular application. So, but again, our focus is on Southeast Asia. So, when we first started this, 8 years ago, of course, there was this system hadn't been run there, so it was a good 5 years to get things running in NWP mode. So, as I said earlier, the rainfall is the priorities 1, 2, and 3 in this part of the world. But again, given the limited predictability of the localized convection, and this Sumatra score, for example, I mentioned, a really fascinating phenomena, the probabilistic approach is essential. So it's very small scale. We've got to be running at kilometer or sub-kilometer. You know, sometimes it's the next 30, 60 minutes in the nowcasting, or maybe the next 12 hours for data simulation, and maybe get to 24 in some times of the year for certain large scale phenomena. But it's really about, you know, the next day and kilometer or sub-kilometer scale. There are some good local observations. We have C-band, S-band, X-band radars, for example. We have Himawari data coming from the geostationary satellites in pretty much above us, and various other satellites. So there is an opportunity for local data simulation. So we develop a system that's called SingV, and it's been operational in MSS since 2019. And just an example there, probability of precipitation for one of these squall events. I think I've shown the top left slide before. It was just one thing we learned during the initial work is that as you probably guessed, actually the most important thing you can the biggest sensitivity we found in our kilometer scale models is what global model you drive it with. So we tested a variety of global models driving the 1.5 kilometer NWP system, GFS unified model, and we're actually now using ECMWF. And that was the biggest, and then that's the difference, for example, between the purple and the orange there. There's the difference between different driving models is actually larger than the differences between the regional models, in this case, the unified model and WRF. And the resolution difference is even smaller when it comes to, obviously depends on the metric, but this is fractional skill score for rainfall over that domain. So you're just emphasizing the importance that we are so tied, and even in the tropics, it's not so mobile as the UK or East Asia, but it's certainly the difference is dominated by the skill of the global model. So the top right is essentially just showing that our automated forecasts, in terms of the metrics that the forecaster uses, is at least as good as what they're producing, and that's without any post-processing. I'll come back to post-processing at the end, but that's without any post-processing, so it's already looking pretty good. And again, this is, you can see this runs from 2019 when we first implemented it. Obviously, this is only to 2021-02 that, but it's continuing to show sort of similar value to the manual forecast, which is all MSS were doing 3-4 years ago. So the numerical weather prediction is very new to Singapore, as it is to many countries in the region. So yeah, there's got the kilometer scale stuff at least. So yeah, it's I think we were in a pretty good place. The proof of the pudding is in the eating, as we say. And the one at the bottom is the fundamental question: what are we adding value on top of the best global weather prediction system in the world? There aren't any other regional NWP systems running that we could consider as good as the global ECMWF, which is going to be at 5 kilometer resolution in a couple of years' time. So, you know, that's the benchmark for us. Can we add value on top of ECMWF in this region? And that's what we call a Hinton diagram with different thresholds of the rainfall, and that's for about 2 years across the x-axis there. So essentially, green is essentially showing that the SingV is producing better rainfall forecasts than the ECMWF in the region. And if it has a black highlighted border around it, that means it's statistically significant. So most of that's statistically significant. I still don't quite understand, to be honest, why we're measuring 0.1 millimeter thresholds of rain. That doesn't sound very sensible to me, but I don't want to take it off because it looks like we're hiding the purple, which is worse. But I can't quite interpret what that means. The important thing is it's the high thresholds, the percentiles, 95th, 99th percentile, that we are really adding value, and that's what's really important, of course, to the stakeholders, that heavy rainfall. Just again, as you can imagine, my data simulation background. We have a few people working on data simulation, including satellite data simulation, and just showing we do the traditional data denial experiments, just showing the various observation types all add value. So what this is showing is that purple is worse. What it means is you take the satellite radiances or the satellite winds or the surface or the aircraft out, and the forecast gets worse, which is sort of what you expect or would hope, that all your observations in doing it this way are adding value. So it's a crude way of doing it. The more modern adjoint techniques don't work in the tropics. It's too non-linear. So we have to rely on these traditional data denial experiments for this kind of kilometer scale tropical NWP, with localized convection being the dominant source of the weather. But it seems to work in our value. Yeah, I probably won't dwell on this too much. I mentioned Himawari, the geostationary satellites sitting above us. We can use a variety of things from that, the atmospheric motion vectors and also the radiuses directly. So we have a bit of a project going on at the moment where we're looking at the Himawari AHI, the humidity sensor, looking at also irradiance assimilation. So Krishnamurti Chandra, who was at OU until last year, he joined us last year from OU. He's been working on this and really hit the ground running with the hybrid 3D bar that we're running at the moment. Ensemble covariances, and just the bottom left is just indicating that we're seeing some value from the assimilation of the AHI radiances. So that's one for the data assimilation people out there. Can talk about that later if anybody's interested. Okay, so that's the weather side. I have to talk about climate change. It is CCRS after all. Yeah, and the usual warming strikes for Singapore. And as I said earlier on the right, the existential threat for Singapore is sea level rise. It's fairly low lying. 30% of the land is less than 5 meters. And if you look at some of the projections, maybe not 2100, but of course sea level rise is not going to stop at 2100. It's going to go on for hundreds of years. And you know, people born today are going to be alive in 2100. What about their grandchildren? So yeah, 2200 is not that far away. And you look at the IPCC results, some of the higher the business as usual scenarios, SSP 585, etc. You're really seeing, you know, potentially up to 5-10 meters. And of course that's mean sea level rise. That's without the waves, etc., that add to those perfect storm, as it were, that might inundate parts of Singapore. So yeah, this is the threat. So Singapore is investing something like $100 billion in defenses for against climate change over the next 50 years. And the way Singapore works, they're all still planning how they're going to spend it. They will have adaptive planning, but they're already planning to spend that much to make sure they can deal with it. And they're planning the future of the city as they'll come through, you know, where the parks will be, where the lakes will be, which way they will align the what they call HDB flats to align to reduce the temperature effect and increase the wind effect and the shade effects. You know, this is all going into the planning, and these models are being used as part of that planning for the future of Singapore in the next 10, 20, 40, 50 years already. So it's quite impressive, the level of detail that goes on. Of course, the climate models are only part of that. You know, the technologies about cooling paints and vertical gardens, that's all part of it too. But you know, with the plans they have, they're relatively confident they can actually get a net cooling, because climate, you know, global warming is about 1 degree here, but they can take 2 or 3 degrees off if they implement certain strategies with cooling paints, with parks, etc. So this is what I mentioned earlier about they have a bit more confidence that they can deal with the temperature effects. And it is hot here. People are used to the heat, but of course you get to certain thresholds, 34, 35, 36, heat stress becomes a real issue with the humidity here especially. So but again, urban heat is the secondary concern after sea level rise. So temperature trend over the past few years, you can see the temperature trend, the daily average temperature, and actually the big jump there between the 70s and past 10, 20 years or so is the urbanization of Singapore. It's not climate change. So again, this is something that maybe Singapore has its own, can do something about. Whereas the sea level rise, of course, is a lot less. Do a lot less about that one, apart from build walls and implement nature-based solutions or whatever it might be. So there's the trace of the various tidal gauges around Singapore, and you can see a trend. It was about 1 millimeter a year until about the 90s, and it's up to about 2 or 3 millimeters a year now, and that's predominantly the global effect of acceleration of Greenland glaciers and Antarctica. It's vertical land movements. Singapore is not like Jakarta or Ho Chi Minh City or Venice. It's not sinking. In fact, it's slightly rising. So the vertical land movement is actually helping a little bit, but it's only a fraction of that that's being caused by the seas rising. So it is a concern. It will be accelerating, as you can see the top right. It has been accelerating, and the projections showed it will continue to accelerate. And the big uncertainties, of course, in sea level rise are about the ice shelf instabilities, the glaciers, Greenland melt, Larsen ice shelf, etc. So, a huge amount of work to be done there. And we do have an Earth Observatory in Singapore, which is looking at those kind of issues, and also looking at paleo records to get a better idea of the tectonics and the recovery from the ice age, which of course may give us some clues in terms of the potential tectonic changes that are going to happen when the Sunda Shelf flips back. It's going down at the moment, it's going up at the moment, but it may flip back with the next big earthquake, and people are a little concerned about what happens then. But that's way beyond meteorology, so I won't dwell too much on that. So so bringing it back to the climate models, the weather models, the seamless weather climate models. So the biggest project in CCRS at the moment is what we call the third national climate change study. So essentially, these are regional climate projections out to 2100, 2150, some of them, using the latest CMIP6 global models, 6 of them as forcing. The previous study in V2 was actually done by the Met Office in collaboration with CCRS, but this time around, CCRS are doing it ourselves. And part of the reason for that is, well, we've got the experience of V2 behind us, but we also now have this in-house SING-V climate model, which has been proven robust in weather forecasting mode. So it's a similar strategy to the Met Office's, if you're familiar with the UK CP18, where they're doing 2.2 kilometre. They did 2.2 kilometre regional climate projections. So here what we're doing for the whole of Southeast Asia is running the larger domain at 8 kilometre and the smaller domain at 2 kilometre. So it's higher V3 is higher resolution than V2, which is at 12. It's a larger domain. It's a much improved model, and the more projections, more a range of CMIP6 global models. So that's number crunching away using supercomputers in both Australia and Singapore. It's the largest project on the National Supercomputing Centre here in Singapore. So it's I think people are looking forward to getting that data, and I think we're about 70-80% through the number crunching. Of course, now we've got a year where all the interesting analysis and product and interpretation comes in. So we've got another year to go with that project, 2023, but we can only do this because we've had this activity where we developed a model that works robustly and been tested robustly around the world by a community of 200 or 300 scientists in Australia or the UK or India and other places. So it's had its tires fairly well kicked. And what CCRS has done is taken it into the deep tropics and tested it and tuned it and fed those tunings back to the broader community. So we're now confident it can be used in regional climate projection mode. So so that's the V3, and I don't have too many results to say, but we have more results in the next 6 to 12 months on that one. I won't dwell on the details. There's a bit more detail on the downscaling. So it's around nearly 3,000 simulation years of for 2,000 for the 8 kilometre and a subset for the 2 kilometre. Okay, so the last part of the talk, I wanted to just talk about, so that's sort of what we've been doing and what we're doing at the moment. I think there are some directions we're going that it's worth just elucidating, which I've mentioned a couple of them already. But again, I come back to this picture we had back at the Met Office. I mean, in terms of modeling, let's talk about modeling and how you're going to use a computer. Well, you can do different things. You can You can look at the resolution. You can look at the better resolving the uncertainty through the ensemble size. You can improve the complexity. You can do more observations, data simulation, whatever it might be. And of course, the optimal combination of which direction you go in these dimensions depends on the application, and it's very subjective. But I'm going to describe some moving in both resolution, complexity, and observations, I think. So the first one is probably, to me, the most important one in this part of the world. I said this is the maritime continent. It's in the name. It's sometimes called the engine room of the global climate system, where the strong solar forcing, the shallow seas, the energy exchange between ocean, land, and atmosphere. There's a huge amount of coupling. We cannot get away with just atmospheric weather forecasts or just ocean only wave or ocean forecasts. So yes, we need to represent these complex feedbacks, and we do that through this environmental model. This in NWP mode, or it's the coupled climate model. So in terms of the system we're looking at here, it's the unified model for the atmosphere. We're running, of course, the joules land surface system, also the hydrojoules in terms of the hydrology and river flow. The ocean system is currently operationally separate. We have a NEMO ocean forecasting system, which is uncoupled from the atmosphere. And there's a Wave Watch 3 implementation sitting on top of the ocean. We don't have biogeochemistry in there yet, but that will obviously, we want to get the basic ocean sorted before we move that far. But one of the goals of this, of course, is that not only do you represent more of the processes that are essential, those interfaces, but you're also providing consistent products for the atmosphere, for the land, for the oceans, for the waves. And so you don't actually need it. I mean, it leads to changes within organizations where, why have separate ocean forecasting, weather prediction, surface hydrology systems when this system necessarily needs to be coupled and is producing all of these consistently. So I think it's in a variety of places around the world. I mean, climate models have been running this way, global climate models have been running this way for a long time. But in terms of weather forecasting timescales, it's relatively new. Global NWP, of course, many of the global NWP centers are now coupled NWP. But for regional kilometer scale, I think it's early days, but that's where we need to be. We're not global modelers, and this is the maritime continent, as I keep saying. So we're not starting from scratch. Just my little glossy little animation of the 1.5 kilometer NEMO system from the UK. And essentially what we've done, as we did with the atmosphere, is to take this system and bring it to the deep tropics to look at the bathymetry. We've adjusted the vertical coordinates to represent the steep shelves that exist off the Sunder Shelf. But essentially it's a NEMO configuration that we can work with the National Oceanographic Centre in the UK, the Met Office, and also partners in France, Mercator and others who are working on the NEMO system. So we've essentially taken this, and this is again kilometre scale ocean modelling. And what we're doing is, these results from the UK, but this is what we'll be doing we just started to do for Singapore. So coupling that, so putting all those components together, I mentioned in the other slide, the atmosphere, the land, ocean, etc. Now the plots here just give us some confidence that this is doing some good things. So if I just explain this plot, so each of the 4 panels is a different season. Yeah, so this is March, April, this is June, July, this is September, October, and this is January, February, and the differences are I've got a zoom panel in the way of the panel here, but so we've got the uncoupled versus the coupled. I think the point I want to make here is that the big difference here in terms of the reduction in error comes when you couple the ocean, where you have an ocean where the diurnal cycle, and this is in the UK, and this happens to be summer, which is when you expect more of a diurnal change in the SST through sunny days, and sometimes you get sunny days in the UK. But that's when you get the impact of the Otherwise, it would just be a daily resetting ocean SST. And with this, it's a dynamic SST, SSH, salinity, etc. And you're actually seeing a better forecast at the surface temperatures because that ocean is interacting and being coupled, and it's evolving through the day. So, and of course, this is the summer. Of course, other times of the year, you don't, like winter, for example, it's very mobile weather. You don't see that kind of ocean atmospheric coupling so much. The system just blows through much too quickly. But of course, if you're going to compare Singapore with any of these seasons, it's going to be this less mobile season. We're in the deep tropics and the doldrums, and so we have some confidence that this is going to actually improve both our weather forecasts and our ocean forecasts. So, for example, representation of sea breezes is something that we just can't do well with the current model. So I don't have any results here. There's a paper there actually, though, that provides some initial results. We initially set it up at 4.5 kilometer. It's now running at 1.5, and so we're starting to look at that. It's not that expensive. The couple system is about 20 or 30% more expensive than the atmosphere only. So it's not a computational cost issue, but it is a complexity issue and a data output issue. So yeah, that's one of the key strategic directions is coupled. So, but I'm sort of running out of time a bit, but I'll just mention a couple of others. One is, of course, Singapore is a city-state, and so as you might expect, urban meteorology, city-scale modeling is obviously very important for this part of the world. So we have again, partly through the collaborations with the UK, where we was back in the UK, back in London Olympics in 2012, we implemented a London model for the London Olympics, and that's continued to work to be run in research mode. It will be operational at some point, but you know, we're taking that configuration essentially, again, tuned it to the tropics, used the obviously things like the local urban fraction, the building heights, the land cover, etc. And some very high, very fine scale land cover data sets here, 30 centimeters over the entire Singapore. We don't need that necessarily in our mesoscale model. But one of the things we're doing with this is running this system in climate mode, where we can provide the larger scales to a microscale model, LES model. It's part of this Cooling Singapore project, and that's with ETH Zurich and Singapore Management University, and it's known as the DUT system, the Digital Urban Climate Twin. So, and essentially what they're doing, that's a digital twin. As I said earlier, they're essentially redesigning Singapore in different scenarios, with different climate scenarios, but also different urban scenarios, how they're going to build Singapore in the next 30, 50 years. And just to look at the sensitivities to building heights or parks or even tree types, and there's a lot of stuff like that going on at the microscale level, but say the CCRS input to that is really the mesoscale. You know, of course, even 100 meters is pretty low, pretty high resolution for us, but these guys want to get street level. Yeah, so just an example of again, this is a very subjective case, just looking at just a run where it's not raining. There's some nice cloud streaks coming from the southerly winds, as I'll show shortly, and these are run with the same number of vertical levels, etc. But yeah, so this is the Sentinel-2 image in the middle there. You can see the sort of cloud streaks with the southerly winds, and actually the two plots either side are the model simulation. It's actually an animation, but I won't run it. And again, I'm not an expert on these kind of resolutions, but you are seeing this is vertical velocity just above just at the boundary layer top, I think. So you're seeing those vertical motions, upward motions, which is leading to those cloud streaks. And again, you can see, again, there may be a bit of spin up coming from the southern boundary. I think some studies were done by extending the boundary further to the south, and it actually just didn't change where the detail and that more chaotic happened. That happened when it got to the land, essentially. So it's interesting. I mean, we sort of analyzing this in a process way rather than it's not producing forecasts, for example. But it seems to be, it's an interesting topic. that will be a real priority for the next 3-5 years in Singapore. Okay, I probably might just my last 2 slides. Yeah. Yeah, I mean, obligatory mention of machine learning in weather and climate science. And I don't say that, I mean, flippant with that, but I think the strategy here is that, you know, to me, we're already doing data science. Data simulation is data science to me. And you know, those who've looked at machine learning, multi-layer perceptrons, deep learning, you look at Hoover norms, you look at minimization algorithms, there's actually quite a lot of similarities between data simulation and data science actually. But having said that, there is a real role for data science, and the top right there is just an illustration of the number of different applications that ECMWF have identified as applications of machine learning. The point being, it's not replacing the whole thing. You're going into the algorithms, the physics of the data simulation, the observation pre-processing, you know, the parameterizations in a radiation scheme that may not be documented anymore and tuned 20 years ago. Nobody quite knows why it's done that way. These are the sort of low-hanging fruit for applications of machine learning, I think. So we've got a few applications there. Post-processing is an obvious one. So my last slide is going to be on post-processing, and this is a relatively old slide, but to me we don't do post-processing of our forecasts yet, because as I say, we've only been running NWP for 2 or 3 years in Singapore. But to me, post-processing is the #1 way to improve your weather forecast if you're not doing it. And this is a slide. This is my favorite slide of the Met Office for years, just showing the skill of the NWP system, the UK NWP system. And it's just, for example, this is a metric that the Public Weather Service uses in the UK, the number of forecasts, the fraction of the forecasts that are correct within 2 degrees at 24 hours. Of course, 1 means they're all within 2 degrees. But you've got the various raw models here, including ECMWF. You've got the global models, you've got the global ensembles, you've got convective scale ensembles. And as we know, they're very variable in terms of synoptic conditions. The weather variability is around 20–30% in terms of raw model skill. You know, in the summer, clear skies, the surface temperatures are really problematic for all of the models. It's not just one, it's all of them. But the role of post-processing is to account for those bias, and this is machine learning, or it could be more traditional methodologies, Kalman filters, etc. But what post-processing is doing, it's providing a bias correction, an intelligent bias correction, but also a blending of the different forecasts. So you take the best from each source of the forecast, from the global model, the deterministic from the ensemble, and you optimize that so your final temperature forecast is actually fairly consistently good. It doesn't have the variations of the raw models, and it's significantly better. Now that black line there, it just happens to be the metric. Or was it 94.5%? We had to beat that every year. So the only way we could satisfy our customers was with post-processing. The raw models just aren't good enough. And there is no physics change, and there's no data simulation change. There's no change of resolution that I think will ever give you that kind of improvement relative to what post-processing can do if you're not doing it. Of course, you know, if you're doing it, then it's a question of incremental returns. But to me, that's the most important thing that CCRS needs to be doing in weather prediction that it's not doing at the moment. And I say that as a data simulation person. I actually shut down 2 data simulation posts and put them into post-processing, which I had a couple of sleepless nights about that, but I think it was the right thing to do, because that's just where the bang for the bucks are at the moment. So on that note, I'll probably just finish and yeah, just summarize. I say this is the maritime continent. It's a wonderful place to do climate science and meteorology. It's not easy. I haven't talked about observations too much, but observations in the tropics, of course, are a challenge. Wind profiles, but also ocean observations. The South China Sea is a big influence around here, and it's one of the most data sparse oceans outside the pole, outside the Arctic Ocean and the Southern Ocean. So for piracy, for geopolitics, because it's a shallow ocean. But we need that to validate our models. We need it for assimilation. We need it for bias correction, a whole variety of things. But observations are a real challenge in this part of the world. So yeah, I think I've talked about the rest of it. So maybe I'll just stop talking there and take any questions. Thank you.
Okay, the floor is open for questions. If you go to Slido, you can enter your question, or you can raise your hand and we can call on you and unmute you. You can ask it in person if you're in voice anyway. Yeah, so Dale, it seems that the going to high resolution, the most obvious effect is the the physiography of Singapore. You see lines of storms. Are they sea breeze or orographic, or it seems like automatic you would get a better, at least climate prediction at high resolution.
Yeah, can you hear me? Yeah. I think that's right. I mean, Singapore is such a small place, and you see it when you're walking along the coast. You see the very local effects, and we see it. We see just rainfall bias, systematic rainfall biases off the east coast of Malaysia, because there's a local hill range there, and there's a sea breeze which is pretty consistent with the cold ocean, and it's yeah, you just have to represent those features to make any progress. So the city scale stuff is a lot of the work there is on the urban canopy representation. So we haven't really looked at the boundary layer too much. I suspect there's some hard stuff to be done there, but yeah, it's but yeah, the resolution and the resolving those features is key.
Yeah. Let's see. So is anybody out there? I think they are.
I hope I'm not talking to myself at 4 o'clock in the morning.
Well, okay. Let's see what else is out there. Okay, well, I think Dale's email and the way to get in touch with him. And are you coming back here anytime soon, Dale?
I've only been back I've only just got over jet lag from the last one after that 16.5-hour flight from San Francisco. It took a couple of weeks to get over jet lag, so I might be a little while before I get back.
Okay, I think we have a hand up here. Let's see. So invite. No. We have a hand up. Hey, Brett, what do I do with that?
Yep, Chris, if you'd like to unmute and ask your question, go ahead.
Hey, Dale, it's Chris.
Hi.
I wonder if you could say a bit more about the unification between the tropical and the mid-latitude physics suites at the Met Office, like how the process worked and what the sticking points were, and that sounds pretty interesting.
Yeah, I mean the original. I think Singapore was to blame for the original fork, because the scheme, the Smith scheme, cloud scheme, wasn't really working in the tropics. It's producing very blobby was a word we used quite a lot. Very intense but very localized, too localized storms. And that was an issue that was ultimately resolved with a bit of a patch, which is to put the PC2 scheme back in again, which was a terrible thing to do in the mid latitudes, but there was no doubting it produced better forecasts, and we sort of kind of wish we didn't do it, because we were sort of getting better forecasts for the wrong reason. So after about 3 or 4 years, some work in Australia, Charmaine Franklin, and also with a couple of people in the APP section, we went through 3 or 4 different versions, which basically ended up in a bimodal cloud scheme, which seemed to be a compromise. At least it didn't make things worse. I think that's often the case in weather prediction. certainly, and maybe it's different in other places, but the Met Office, the climate is often the dominant partner. And often you want to do it for the right reasons and get the right climatologies and climate signals. And if you don't make the forecast worse, then that's good enough. So, you know, as you probably know, there were a lot of the improvements in weather prediction have come from data assimilation or other things, but the physics was a 5-year effort just to get the cloud and the tropical precip better at the same time as getting the mid-latitude temperatures better. So it was a long old haul. But yeah, that was it in a nutshell. I don't know if that
Thanks.
helps.
We have a question from Bill Quo. Bill, if you'd like to unmute and ask, go ahead.
Hi, Dale. Thank you
Hello.
for the great seminar. And I have you showed the comparison between the different models in terms of precipitation forecast, UK, unified model versus WRF. But we all know that, like, for example, WRF have many choice of physics, right? So sometimes you say, hey, is doing better than WRF. The question here is, it depends on how well you tune the physics, isn't it? I mean, we could probably tune the physics to make WRF better than right? Anyway, I'm just interested in your comment on that. I do actually have a second question later on after you answer the first one.
Yeah, I don't think it was you can always make the forecast, the WRF better. I think it was the decision to use the wasn't so much based on just that. It was it was partly the data assimilation, actually. At the time, there was at the time it didn't look like there's much resources in WRF DA, funnily enough. Whereas convective scale 4D VAR was, and had 30 people working on convective scale data assimilation at the Met Office, and it was like, well, we need to be part of that. And so it was a broader decision than just the performance issue. I think I will say, though, I didn't mention it, we are actually we're running WRF in those regional climate projection models for a bit of to get in a bit of regional model uncertainty. So we've contracted with the local university, NUS, who are running downscaling WRF. So we have some so we have a sort of sample there of UM and WRF, but that's in regional climate projection mode, not in weather forecasting mode. We've switched WRF off for weather prediction mode.
Okay, well, thank you. My second question here is I'm glad that you recognize for weather prediction, even for climate studies, South China Sea is a major data void region. And it's really not totally data void because, for example, you actually do get good radio occultations observations from the various soundings. And Cosmic 2, right, for example, has a significant number of soundings over the tropics.
Yeah.
I think if I wonder what is the status of Singapore in trying to make good use of those observations to improve both your regional and convective scale predictions.
Yeah, I mean, when I was talking about the data void, I was actually thinking about the ocean, because that's if you look at the surface buoys or there's no Argo flights because it's a shallow sea. The ocean is very poorly sampled. Obviously, you get the SSTs and whatever from space satellites, but I was referring to the ocean. Yeah, there's a lot of data in the atmospheric side of thing, yeah. So as we talked about a few weeks ago, right, we have a look at the ECMWF map with all the private sector occultation data plus Cosmic 2 and everything else. There's actually quite a lot of data there. So yeah, I think that's on the list. I'd say the priority in terms of our priorities. I think the radar is the #1 priority. And we don't have a big team, so what we're actually doing at the moment is focusing the resources on the DA techniques, because better, as you know, better DA improves all the observations, and it's wasted time if you don't have the covariances or the DA technique working. You're not going to get the benefit from the obs that you really want. So it's a strategic decision to really, when we're not going to run 4D-VAR. We decided we're not going to do 4D-VAR. So it's at the moment we're developing the hybrid, plus also centering the ensemble around the high resolution 3D-VAR hybrid analysis, where previously it was just a downscaler. So we want to focus. We've only got 3 people working on this, so we want to focus those people on the DA and the ensemble, and then hopefully when we're more confident in the tropical configuration of the DA, then we can start adding additional observations. But as I said, I think radar is the key for us, because there's a lot of good radar data around here, and it really is the next 3 to 6 hours that we're really aiming for. So then again, you bring in nowcasting too. So it's a judgment that we're not so interested in the large scale 24-hour forecast. We're really looking at the fine scale, very short range. So I guess that all those things factor into the, but yeah, there are some good atmospheric observations out there, definitely.
Well, with that, I think we're out of time. And Dale, I want to thank you again for coming in from live from Singapore at 4 in the morning, now 5 in the morning. And yeah, thanks so much. Interesting seminar, and welcome you back here sometime in the future.
Look forward to it. Okay.
All right.
Thanks all.
Bye-bye.
Good night.